Okay, so we are continuing with the example. So let's say that at the beginning of this problem, I'm given this velocity distribution, V distribution of this target. Maybe something like this. You know, it has positive velocity. Now this, let's say, it's a symmetric distribution. Its mean value is something like that, V bar. So it's something like a Gaussian or something like that, but it's symmetric. So at the end, what do I see? I see the power spectral density, something like this. So for this, you know, kind of a signal, so let me write this power spectral density. Let's say draw this J omega. This is, I apologize, this is supposed to be continuous time. Okay, I have something like that, J omega. So what do I see is, again, the scaled version of this. So this, let's say, omega bar. Okay, but you know, not very much different. Maybe its width is different because of the scaling. It's just shifted to another location and so on. Of course, it's multiplied by some number, etc. Okay, that is it. So what is, you know, your guess? The area under this power spectral density. Area under this. Okay. So remember, our process was, you know, I should calculate this, isn't it? The integral of this with respect to omega. So how can I calculate? So there's a shift operation, omega naught. So this shift, okay, the area under SS J omega, okay, minus infinity to infinity. I should have a square C over omega naught. So I have this density C over omega naught minus omega d omega, isn't it? So I should calculate this integral. Now let me call this omega prime, if you wish. Okay. If that is omega prime, then dw or d omega is equal to d omega prime. Okay. Or minus of it. Then this becomes plus minus. Because of this shift, yeah, that is it essentially. This becomes omega prime. Now, after that, let me call this, let's say, nu. Okay. So my new variable is C over omega naught, omega prime. So d nu is C over omega naught, this. So then this and this becomes d nu. Okay. And so this is just area under this density with the variable nu times magnitude a square. Okay. That is it. Well, no surprises, because do you remember at the beginning we have defined it something like this: a e to the j omega naught t divided by omega naught, t minus r of t divided by c. So what's the power of this? What is the magnitude square of this? So the magnitude square of this is always a square. Okay, whatever happens to the face. So I get that one. So the power of this one is as expected. So it tells us that we are doing something right. At least we are not getting obvious mistakes. Very good. So what else? I'm erasing this. Well, what is the center frequency? So the center frequency is the location of this peak. Okay? It is, you know, because it's just nothing but the shifted and scaled version of this. So you may say that this density has a peak location. So this is the same peak location. It has to be the same because it's a unimodal density, as you see. If you scale that unimodal density, you get something else, but the peak location will be just a scaled version of each other. So if this density, well, how should I write this? F V of V bar is the peak location is the peak value of the density. Okay, then SS, this one, J omega has the peak at, well, then the argument of this function, somehow it has to be equal to V bar, isn't it? Because if the argument is V bar, this function is maximized. Okay, peak at, let me see, C over omega naught minus omega, this is special omega, is equal to V bar. Somehow, if I select this, these are all constant, omega bar, somehow specially, now this should be equal to, the whole thing should be equal to V bar. So, this is just, our thinking. Then omega bar is equal to, omega bar is equal to omega naught minus omega naught divided by C V bar. Okay, move this to this side, omega naught divided by C, this goes here. Okay, so this is equal to omega naught 1 minus V bar over C. Okay, actually this is nothing but the Doppler effect, as you see. Again, the units match. This is in, let's say, radians per second. This is velocity meter per second cancel. Okay, so units match, and this is what we call the Doppler effect. So this is the center Doppler frequency due to target motion. Target, let's say, motion or velocity. So this is the mean target velocity. So we get something like this. Okay, Doppler effect at that. So actually this is called, you may say, this Doppler spread. Doppler spread of this target. So in many applications, maybe this is like a Boeing jet, or this is like some other kind of F-16 jet and so on. They have different kind of Doppler spreads. By looking at this, you are collecting data, and you are looking at the spread of this, you can tell what is going on. Okay? Maybe you can identify the target and so on. Okay, so this is the mathematical model, and this is indeed the Doppler frequency shift. Okay, very good. When V is equal to 0, of course there is no shift, it's just reflecting back. But if target is approaching towards us, now the frequency is increased, because, or decreased, depending on, the sign of this V, how we take it at the very beginning. Okay, something like that. But in the actual case, if the target is approaching towards you, frequency is increased. Okay, if target is approaching without, any sign issues, target is getting closer to you, then Doppler shift is, incoming velocity will be increased. Okay, so what else I can say about this? Well, that's all for now. Okay, now let's have a second example, but this is more like a numerical example. This is from, let me see, HIS 3.4.1. This is more like a computation example, but this is also important for our purposes. So as you see in this course, the concepts are somewhat difficult, because we are sometimes discussing the physics even of the problem, and there is Fourier transforms, power spectral densities, autocorrelations, usual densities, they're all mixed up in these calculations. So you have to be somewhat knowledgeable in these topics. But it's not very difficult. And in the other part of this course, this is also fundamental for us, but this is, you will see, mostly computation. But, as a DSP professional, you have to do these computations. Otherwise, who will be doing these calculations? 1 over. Okay. So this is, again, I'm given this. First of all, what's going on? So input is a Weissan stationary, no surprises. And output is, we know that it's Weissen's stationary, but the goal is find output autocorrelation. Okay. Again, I will use transform domain calculations as we did, but this time I'll be using Z transform. Okay. So how can I do this calculation? First of all, do you remember Z transforms, etc.? So I want to briefly discuss this. If I have x of n, its Z transform is x of c. Okay. And it is defined as x of n, z to the minus n, minus infinity to infinity. So many students, maybe at the beginning of their, when they first time meet these calculations, they sometimes forget that z is a complex number. Okay. So what does it mean? This summation is an infinite summation. It may diverge. Diverge means it's practically useless for our purposes because you are getting plus or minus infinity, and if you add anything to plus or minus, or subtract anything to the plus and minus infinity, you get again infinity. You are losing information, okay? Because you cannot see what you have added or subtracted. So convergence of this summation is, infinite summation is, critical for us. This is called region of convergence. And you may remember in Z domain, there is this unit circle, okay? And if we have, let's say, pole discussion, inside the unit circle, then we say that if, okay, let me take it back. If I have poles over here and another pole over here, surprisingly, I'm drawing good enough circles. Okay, now you can say, now how many rings do I have? I have blue shaded part, I have red shaded part, and I have this outside of this. So red, blue, and green. Okay, I have 3 parts. Now region of convergence can be, let me call this 1, it can be 2, the intermediate disk you may say, and this is the outer part, 3. Okay, so one thing to remember, region of convergence never includes a pole. Pole is divergence. At this point, this summation diverges, we know that. And similarly, it diverges, it may diverge or may not diverge on the unit circle that this pole is located. So this is the boundary, and we don't discuss what happens on the boundary in general, but it may diverge or, we don't know, converge on this boundary, but it's not an important, very critical result for us. But for the other cases, region 1, region 2, region 3, what we call is, we have, region of convergences, okay, for x of z. Now, in a given h of z, not only this, you have to be provided by region of convergence. For example, this region of convergence, 3, third one, it tells us that this region of convergence does not include unit circle. Unit circle is this one. Let me see, do I have anything else? Let me have this then, unit circle. Unit circle is this. Okay. So this is 1 minus j. So unit circle is included in region number 2. Okay. Unit circle is only included in the intermediate disk. So if we are in region number 3, we know that, this is a causal sequence. This is what we can say. But this region does not include unit circle, meaning that I cannot calculate the DTFT, discrete time Fourier transform of this sequence. So I cannot calculate it. So it is unstable but causal. In region 2, it includes this unit circle. You can say that this filter is stable, okay, because I can calculate this DTFT, impulse responses Fourier transform. In which sense? In the sense of L2, or energy sense, let's say. Okay. And then this is double-sided because it's not extending to infinity and so on. So again, this is an unstable case, and this is anti-causal. So this is our Z transform knowledge. And this, by looking at this region of convergence, or with the knowledge of this, I can say so many things as you see. But without this region of convergence, I have no idea about what to say for this one. Okay. But let's say that some region of convergence for this one is provided. Maybe this has a pole at, okay, H of Z has a single pole at 1 over 4, am I right? When Z is equal to 1 over 4, Z inverse is 4. So as you see, I have divergence or singularity, you may say, at 1 over 4. Z is equal to 1 over 4. Then for this one, there's only one pole, 1 over 4. So either inside of this or outside of this. So I have only two possible region of convergences. You will see it's not very, critical for our example, because you will immediately see why that is so. If you don't remember these Z transform discussions, I highly recommend you to check them, because these are just some brief notes, and you should remember them. If you are a signal processing professional, you should remember them all the time, because these are very basic. Make sure that you know them well enough. So what was I going to do? I was going to calculate this Ry of k. So let me start solution. So how can I calculate this? Ry of k is Rx of k. Oh, okay, I don't know anything about x. Let me explain. Convolution with h of k. Okay, that's something like that. Convolution with h of minus k. Okay. So let's say that in this problem, this is white noise with variance, let's say 1. Okay. Then Rx of k is delta k. No need to do convolutions because it's identity convolution. Okay. Then I have h of k, h of minus, I should put conjugates over here, but since this is real valued, well, you can see h of n with some experience, let's say earlier experience, h of n is real valued. Okay, I have this. So I will try to do this calculation in Z domain. So I will call this S y of C, Z transform of Ry of k. Okay. So this is then Z transform of, well, well, let me see, Ry of k, this is this, okay, let me write it in a different way. Then, Sy of Z, power spectral density in Z domain, convolution, I'm just writing this convolution identity, H of C, H conjugate 1 over Z conjugate. Okay, from our earlier knowledge. Now I'm calculating Z transform. Okay, now I want to do Ry of k calculation, which is inverse Z transform of Sy of C. Okay, that is it. Inverse Z transform. So inverse Z transform of h of z, this 1 over 1 minus 1 over 4 z inverse times. Now if everything is real valued, you don't have to worry about these conjugates, okay? Or they will be canceling each other. You write conjugate over here, you take one more conjugate, then they cancel. So these conjugates are important, especially important, if these coefficients are complex valued, okay? But these coefficients are not complex valued, so maybe I didn't have to write these conjugates because I'm getting the same result. 1 over 1 minus 1 over 4z. Okay. Instead of z inverse, I'm writing 1 over z. Inverse cancel, so I get this one, 1 over 4z. Now this partial fraction expansion, so I will, just for the sake of simplicity, I will call this, I don't want to make mistakes at this point, let me call this z inverse, z reciprocal, zr. But this may look like real. Z, let me say inverse. Okay, so that is it, z inverse. So then this becomes z inverse to the power minus 1. Am I right? So I want to do partial fraction expansions with z inverse. So this is z inverse. Now, so I have z inverse variable over here. So if I multiply numerator by minus 4, okay, then denominator by minus 4, I get this. Is this correct? Minus 4 is there. Minus 4 times 1 is this. Minus 4 z inverse. Okay. How about this one? Now I'll be multiplying this one by z inverse first. Okay. Okay, this is done. Z inverse minus 1 over 4. I multiply the numerator by z inverse, denominator by z inverse, meaning that's zi. Zi minus 1 over 4, so they cancel. The reason I am doing this is, it's easier because, okay, the reason that I'm doing this is this. What was that? Sorry. I have some Z transform pairs that I want to use. Z transform of alpha n un. Okay, this is the causal part. 1 over 1 minus alpha z inverse. Okay. So this is the Z transform of minus alpha n u minus n minus 1. That's right. Is also equal to 1 over minus alpha z inverse. So this is one of the first things that you learn. So if you only know the right hand side, you see that there are two different time domain sequences which have the same, Z transforms expression. But their region of convergence is different. And you can understand their region of convergence from our earlier discussion. So this is a causal sequence. So its region of convergence includes infinity. Okay? So this is an anti-causal sequence. This region of convergence includes 0. Okay? So it's like going in towards this origin. Okay? So by looking at this, so this one, for example, has a region of convergence, maybe 1, something like that. The other one is like 3. It's going to infinity. So you need this region of convergence, but so as you see, these ones are terrible looking like that. So I want to use them in my, Z transform calculations or inverse Z transform calculations. Okay, so I'm at this point. So this is equal to inverse Z transform, partial fraction expansion. Okay. So how do you do this partial fraction expansion? You cover this, then you do this calculation. So this is minus 4 times 4 divided by 4 minus 1 over 4. So this 3.75, or let me say 15 divided by 15 times, let me say, times another 4. Okay. Minus 4 times 4. So I'm inserting instead of Zi 4. Minus 4 times 4. So this is 15 over 4 over here. So 1 over of it is 4 over 15. Okay, that is it. So how about this one? Now this is absent. Minus 4 times 1 over 4. Okay, that's good. So 1 over 4 minus 4. So again, this is minus. Okay. Minus 15. 16 minus 1 minus 15 times 4. So I have another 4 over here. So this 2 cancels. I get something like that. Okay. Let's see what will happen. So then this is inverse Z transform of. So let me go back to usual business. So this is what? 16 minus 64 over 15 divided by this Z inverse minus 4. So I want to recognize something like this. This is the reason that I use ZI, because I want to have forms like this one. Okay. Plus, this is negative, this one is plus, this is 4 over 15. And this one is minus 1 over 4. Okay. Okay, it's almost like in that form, but I need a 1 over here instead of 4. So what should I do? Well, let me do one more step then. So I'm dividing by minus 4. So this is 16 over 15. I'm dividing by minus 4. 1 minus divide by minus 4, or multiply by minus 1 over 4. Okay. Plus, then multiply by minus 4 both sides. Minus 4. Okay, so I get something like this. So, what's going on? Okay, this, that, okay, I recognize this. This is alpha is equal to 1 over 4. This is alpha is equal to 4. But which one I'm going to use? Because alpha is 1 over 4. It can be either this or that. I don't know. So what am I going to say? Well, what do you think? Well, the answer is this. Ry of k is a double-sided sequence. What do I mean? So it's something like this. If I have some value, 1 is equal to minus 1, 2 value, let's say this is equal to minus 2.5 at 2, then at minus 2 it's also minus 2.5. So in other words, Ry of k is equal to Ry of minus k. There's a conjugate also. They are complex conjugates of each other also. So they are Hermitian symmetric, but for real sequences, they are just even symmetric, as you see. Okay. So what kind of region of convergence such sequences have? This is not causal, as you see. This is not anti-causal. So it is, located in the ring. This is the reason that this region of convergence is not even stated. Because this autocorrelation is supposed to be in the ring. Okay? It cannot extend to infinity because it cannot be a causal sequence, because it has to have such a symmetry for all k. So this autocorrelation sequence is in a ring. So if I check this pole zero diagram of this, so what do I have in the pole zero diagram over here? So I have a pole at 1 over 4. And this is, do you remember we have called this complex conjugate, not complex conjugate, conjugate reciprocal pair. Okay? So these are the conjugate reciprocal pairs. Previously we have also discussed this. So if I have a pole at 1 over 4, then because of this multiplication, where is that one? So this is h of z times h of 1 over c. So if I have a pole at 1 over 4, when z is equal to 1 over 4, this diverges. So this argument is 1 over 4 when z is equal to 4. Okay? So this combination of these two terms has two poles, which are at conjugate reciprocal locations. Okay? That is it. So where is my region of convergence given this discussion? Well, this is another boundary. This is another boundary. So my region of convergence for this inverse Z transform calculation is, it is this region. So on the real axis, in between 1 over 4 and 4. Okay? Very good. So this one will be 1 over 4. This is the pole with 1 over 4. So this is this one. So I'm on the right side of this. So this will be giving me the causal part. Okay? The causal sequence. So if I write my final result, let me erase this then. So as you see, there is some computation going on, but it's not terribly complicated. You just have to be careful. Okay? So this goes on. Let's say over here, this is equal to this term. This term has a pole at 1 over 4, and for this region of convergence, with respect to this term is the causal part. Okay? So this is the causal relation. So 16 over 15. Okay. And 1 over 1 minus alpha, 1 over 1 minus alpha Z inverse, 1 over 4 to the power k, because this is autocorrelation, u of k. Okay. The other one, so this is the anti-causal part. This is equal to minus, or that minus cancels that minus, again 16 over 15, and I have, this is at 4 to the power k u minus k minus 1. Okay, so this is the anti-causal part, because this term, when inverse Z transformed in this region of convergence, corresponds to this. Inverse Z transformed, it corresponds to that. Okay, so this is the end of this example. This is Ry of k. But as you see, you have to be, very knowledgeable in these Z transforms. Otherwise, you cannot complete this without making a mistake because of this region of convergence discussions, because of these, deep understanding of effect of region of convergence and causality, autocorrelation properties, and so on. So if you check this, now let me try to sketch this, but let me briefly calculate this. Ry of 0 is what? Ry of 0 is 16 over 15. Okay. Ry of 1 is, so when k is equal to 1, this is 1. So this is 4 over 15. Okay, this is good. This is u of minus 2, this is 0. And similarly, this is supposed to be Ry of minus 1. So when k is equal to minus 1, this is 0. Don't worry. This is 1. This is minus 1. Okay, 4 over 15. At least that matches. Then Ry of 2 is, this is supposed to be minus 2. And if I have 2 over here, 1 over 15. If I have minus 2 over here, again 1 over 15. So I see the following. Maybe there is an easy way of writing this. It is this. 16 over 15, 1 over 4 to the absolute k. And no surprises, because this is supposed to be an even sequence. If I sketch this, 16 over 15, this is 4 over 15, 1 minus 1. This is 2 minus 2, 1 over 15, and it goes like this, 3 minus 3. This level will be 1 over 60. Okay? Because at every k you are dividing it by 4 at every increase of k. Okay? But what we see is this indeed an even sequence. So it seems that we have done a good calculation. So we get reasonable answer for this problem. Okay. Okay, so let's see. Okay, so that's all for this hour. So we will continue from this point on with the discussion of different types of random processes. What do I mean by type? So as you see, this is a one-pole system. So I may have poles and zeros, only zeros, etc. And I will analyze different type of such power spectral densities when what happens when I have zeros in addition to the poles, and how it will affect the spectrum, etc. We will discuss such things in the next hour. So that's all for today. Thank you.